Hey, we're recording. All right, so today's the 5th, right? Okay, today our topic, and this is the last topic in chapter 8, is L'Hopital.
Mr. Brown, was that some guy's last name?
L'Hopital, yeah. So L'Hopital's rule and comparative rates.
Now,
Okay, so getting into L'Hopital's rule, we're going to talk about indeterminate forms. Who remembers, by the way, from chapter 1, was it 1 or 2, the limit as x goes to 0 of sine of x over x? That's 1, right? How did we determine that it was equal to 1? Way back then.
you said so.
Well,
It was Mr. Brown's rule.
I know I said so, I know I told you, but there was also one more, there was another method that we used to kind of, like a visual method so that we could kind of prove that that was the case. What did we do? We graphed it. So we looked at it on the graphing calculator, and it definitely was equal to 1. Well, today we're going to look at mathematically why this is the case. And in doing so, we're going to cover, take a look at indeterminate forms. So if the limit as x goes to 0 of f of x over g of x is equal to 0 over 0, then this is an indeterminate form. And that's actually what happened in this case with sine of x divided by x. The sine of 0 is 0, x of course is 0, you end up with 0 over 0. So indeterminate just means that on the surface, you're not able to say exactly what it is, so you may need to do something else. Another indeterminate form is if the limit as x goes to infinity of f of x divided by g of x is equal to infinity over infinity. So those are indeterminate forms there. No, not necessarily. No. It could be infinity. It could be 0. You just don't know. And I think we talked a little bit before about the concept of infinity, and that there may be something growing at a faster rate than another thing. Like y equals e to the x grows at a much faster rate than y equals natural log of x. So you may have a bigger infinity over it. So in that case, you can't say it's just 1, because it wouldn't be. So, but we'll take a look at that, and that's a good question, because you do have problems on the FRQs on the AP exam that explicitly deals with that concept.
So like when you said infinity plus 1 is greater than infinity.
Wouldn't it just be a double indeterminate?
Huh?
Because it's 2 zeros over 2 zeros.
Maybe.
Got it?
All right, so here is L'Hopital's rule. It says that the limit as x goes to 0 of f of x divided by g of x is also equal the limit as x goes to 0 of f prime of x divided by g prime of x, which is also equal to the limit as x goes to 0 of f double prime of x over g double prime of x. And we can actually play this game many more times if we need to. That's just nothing. Okay, so here, if you take the limit and you end up with an indeterminate form, then you can apply L'Hopital's rule as long as it's set up as a quotient. So it has to be the limit of, as x goes to 0, of f of x over g of x equals 0 over 0. So it has to be already in the form of a quotient. Now you may have to play around with the algebra to get something in the form of a quotient, which you can do easily. And we'll take a look at those types of problems as well. Any questions? All right, let's take a look then. Let's go ahead and revisit our limit as x goes to 0 of sine of x over x. Okay. So we end up with 0 over 0. That's indeterminate. So then that's the same thing as the limit as x goes to 0. Well, what's the derivative of sine of x? Come on, don't be afraid, yell it out. Cosine of x. And the limit, the derivative of x is just 1. So now we have the limit as x goes to 0 of, so here we have f prime over g prime. Now when we plug in a 0, we get cosine of 0 over 1, which is 1 over 1, which is 1. Which is what we knew way back in August when we took a look at the graph. So L'Hopital's rule actually allows us to do this. Okay, let's take a look at another example. Okay, how about this one? Okay, the limit as x goes to 0 of cosine of x minus 1 over x.
There's also one at 0. Right?
Is it cosine of x minus 1 or cosine of x minus 1?
It's no, it's cosine of x. It's cosine of
Oh, okay, so it's separate.
Why? Why would he know?
so it's cosine of x, quantity cosine of x minus 1. Okay, so here when we substitute in a 0, cosine of 0 is 1. You get 1 minus 1 over 0. You end up with 0 over 0. So this is the indeterminate form. Now, way back in chapter 1 when we dealt with the sine of x over x, we also took a look at this one. And some of you were saying 1, some of you were saying 0. Which one is it? Is it 0? Well, let's take a look. Well, because you have the indeterminate form, it's the same thing as the limit as x goes to 0. Well, now we can take the derivative of cosine, which I believe is negative sine x. The derivative of 1 is 0. All over the derivative of x, which is 1. So you get negative sine of 0 divided by 1, or 0 divided by 1, which is 0. Okay, so with our indeterminate forms, we can go ahead and evaluate in this manner. Okay, now let's take a look at an example. You may or may not recognize this, I'm not sure. But what's the limit as x goes to 3 of e to the x squared minus e to the 9th all over x minus 3? And this, I believe, is from chapter 2 or 3, I'm not sure. But honestly, on the test, I would expect this to be a 15-second at most problem.
You're wrong.
I really would.
We all know that's not.
So when we plug in the 3, okay, we'll go ahead and take a look at it L'Hopital, and then I'll remind you guys. Does anyone remember where you've seen this before?
It looks familiar.
Yeah. I think I've glanced at it.
Huh?
We didn't skip that problem.
How about the alternate form for the definition of a derivative?
Oh.
No, I'm just kidding.
No.
No.
The limit as x goes to c
Okay.
of f of x minus f of c over x minus c
Oh.
is the same thing as f prime of c.
Yeah,
Okay, but let's say on the AP exam you forgot that.
That's the rules still.
No, let's say you forgot that and you were not able to. You were not able to come up with this answer in 15 seconds. Well, if we plug in our number, then we're going to get e to the ninth minus e to the ninth over 3 minus 3. So you end up with 0 over 0, indeterminate form. Okay. So now what we do is, let's go ahead and take the derivative. So this is the same thing as the limit as x goes to 3. Well, the derivative of e to the x squared is 2x e to the x squared. The derivative of e to the ninth is what?
Negative.
Isn't it 9 e to the eighth? It is 0. E to the ninth is a constant.
Oh, yeah.
It's a value. It's like 2.71 to the ninth power. So the derivative there is 0.
And two.
So on the bottom, the derivative of x is 1. The derivative of 3 is 0. So now when you plug in your 3, you end up with 2 times 3 times e to the 3 squared, or 6e to the ninth, and that's our answer. Okay? Now, if we had remembered from before the alternate form for the derivative definition, then what you would have recognized is that your function, first off, you're looking for f prime of 3. That's what you're looking for. But f of x is equal e to the x squared. And then all you need to do is take the derivative of e to the x squared and plug in 3, and you have your answer. F prime of x is 2x e to the x squared, and then f prime of 3 is 6e to the ninth, which is what we got here using L'Hopital. All right, so how do we compare f of x and g of x?
F of x and g, f of x, f prime of g of x equals x, no one. Right?
Well, we talked before about the L'Hopitals if it's indeterminate, but oftentimes you're able to determine what the answer could be without actually applying L'Hopitals. Okay. So here's a little rule to follow. The limit as x goes to infinity of f of x divided by g of x is going to equal to 0 if g of x is greater than f of x. So if g of x is increasing at a much faster rate than f of x, then basically what you're doing is you're dividing a smaller number by a much larger number, and that limit as x goes to infinity will be 0. The limit as x goes to infinity of f of x divided by g of x is equal to infinity if f of x is greater than g of x. So if f of x is your larger function, then it's growing faster. All right, so let's take a look at an example. I'm going to use that concept. Let's say, by the way, here the growth rate or growth speed for your functions are polynomials. They kind of grow at a medium speed. Logarithmic, is slow speed. And exponentials, fast speed. So the exponentials, they grow at a much faster speed. So the polynomials are the medium, the logarithmics, really slow, and the exponentials, they grow really fast. So kind of like an example for the 3. So here we have our polynomial. And then we have our logarithmic. And we have our exponential. Okay. So let's take a look at an example. What's the limit as x goes to infinity of x cubed divided by e to the x? Now, as x goes to infinity, both of those functions, f of x and g of x, they're going to infinity. So you are going to get f of x over, you're going to get infinity over infinity. It is going to be an indeterminate form. Okay, but if you can recognize one function as growing markedly faster than the other, then you may be able to avoid L'Hopital's. So taking a look at these two, which of these two functions grows faster? The e to the x. So your answer should be 0. Okay, so it should be 0. So let's check it out. Okay, we get infinity over infinity, so well, we need to take the derivative with L'Hopital. So limit as x goes to infinity. So then this is going to be 3x squared over e to the x, which is infinity over infinity. Oh, now we have to do it again. So this is the limit as x goes to infinity of 6x over e to the x. Well, that's going to be infinity over infinity. Well, now we have to do it again. That's the limit as x goes to infinity of 6 over e to the x. So now this is going to be 6 over infinity, and that's 0. Now the issue that I have here is, yeah, we were able to do L'Hopital's rule, and it really only took us 3 steps to get our answer. But what if this had been x to the 310? Are you really going to do L'Hopital's 309 times to find your answer? I don't think so.
If I really didn't know to do that really quickly.
So if you're able to conceptually understand that the exponentials grow at a much faster rate than the polynomial, then you're able to apply this logic. So there are going to be some problems where you're not going to always want to use L'Hopital's. If you're not sure if you have one function that's greater than another, then you want to go ahead with L'Hopital's. But if you know for sure, like logarithmics, those are always slow. And if you have an exponential compared with a logarithmic, the exponential is always going to be larger. Okay. All right, let's go ahead and take a look at another example. All right, let's take a look at an example. Here is number 38 from page 585. All right, so we're taking the integral from 0 to e of natural log of x squared dx. Okay. Now, with this particular problem, it is an improper integral because you have an infinite discontinuity at 0. If you remember the graph of natural log of x, it's like that. So it's indeterminate at 0. So 0 provides an infinite discontinuity, so you are going to write it or treat it as an improper integral. So we need to rewrite this as, well, first off, the natural log of x squared, I would hope that you all would rewrite this as just 2 times the natural log of x. Okay. And I think if you do that, that'll be a little easier. So this then becomes 2 times the integral from 0 to e of ln of x dx and that's equal to 2 times the limit as a goes to 0 from the right, because remember your limit is your discontinuity. So as a goes to 0 from the right, the integral from a to e of ln x dx. So that's 2 times the limit as a goes to 0 from the right, and then the antiderivative of natural log of x is just what? Ooh, I'm impressed. That's awesome. So x ln x minus x, and we're going to evaluate that at e and at a. So when we plug our values in, that's 2 times the limit as a goes to 0 from the right. So that's e, natural log of e minus a ln a minus a. So for the first term here, you have e times the natural log of e. So that's e times 1 minus e. So that part right there will zero out. So what we're going to end up with is 2 times the limit as a goes to 0 from the right of the negative a natural log of a minus a negative a. So that's just going to be a minus a ln a. Okay, now when we evaluate this limit, this will be 2 times 0 minus 0 ln 0. Well, this is 0 minus 0 times negative infinity. And this part right here, we haven't talked about it, but this is also an indeterminate form. So this 0 times infinity is indeterminate. All right, so we need to use L'Hopital's in here somewhere. So we're running into a problem where you have the a ln of a, because that's the part that's generating the indeterminate in the 0 times infinity. So in other words, we're doing our improper integral as fit. When we get to this part right here, it's an indeterminate form, and now we need to apply L'Hopital's. Right, so we're going to have, and we're only, this part right here is going to be 0. So we're okay here. That's not an issue. It's this part right here we need to deal with. So 2 times the limit as a goes to 0 from the right of a times ln of a. Now I don't know if you guys remember before I said with L'Hopital's we need to make sure that it's written as a ratio, as a fraction. And here this is a product. Is there any way we can rewrite this so that it is written as a ratio? Factor out an a. Is a the same thing as 1 divided by 1 over a? So we can rewrite a as 1 divided by 1 over a. So then this just becomes ln of a all over 1 over a. And that's why I was saying before, really any type of problem you can make it fit using a little bit of algebra, you can make it fit into a ratio. And when we substitute in the 0 here, it is still going to be indeterminate. But now what we can do is we can go ahead and take the derivative. We can use L'Hopital's. So if we use L'Hopital's, I'm sorry, but I made a mistake earlier. This right here is a negative. Does anyone know why that's negative? Because it's 0 minus that. So it's 0 minus the limit here. So that's why that's a -2 now. All right, so this is when we substitute in our values here, the limit as a goes to 0 from the right, what we're going to end up with is the limit of natural log of a is -infinity, and 1 over 0 gives us infinity. So you have -infinity over infinity, which again is indeterminate. So let's use L'Hopital's. And for those of you who have taken French, why do I want to put that little caret thing over the O?
It's the accent.
For the accent? Okay, whatever. Okay. I'll take your word for it.
It would sound like without the accent.
All right, so when we take the derivative, we get -2, limit as a goes to 0 from the right, and what's the derivative of natural log of a? I'm sorry. What's the derivative of natural log of a? 1 over a.
Or 8.
And how about the derivative of 1 over a?
That's negative 8.
So we have 1 over a divided by -1 over a squared. Well, that's 1 over a times -a squared over 1, which is just a. I'm sorry, -a. Okay, so here's what we have. We have -2, and the limit as a goes to 0 from the right of 1 over a divided by -1 over a squared is the same thing as the limit as a goes to 0 from the right of -a. So our answer here is going to be -2 once we plug in the 0 for a times 0, and our answer is 0. So this problem all the way in the beginning here, the integral from 0 to e of natural log of x squared dx, it was in fact improper. When we went through all of the steps, we did determine that the answer here is 0. Okay.